if you're here just to check out the formulas and I'm not going to listen to the explanations, you can just pause the video here. Here's a quick recap on the intersections and reflections. That you can choose to use as your collision detection and collision response in a simple 2D program. So intersections and reflections here. To begin with, let's just cut to the chase and write up the formulas for the intersection and for the reflection. So if we begin with the intersection, even though we covered that later in the lecture, we're going to look at an array that has a point A and a vector C, and that's set up in the parametric form. P of t equals A plus t times C. That's not great. T times C. On the other hand, we have a point B and the normal vector n, and this represents the line or the plane. I'm going to draw it in 2 dimensions as a line, but this could represent a plane in 3 dimensions. The line or the plane that the ray can collide into. So that's not exactly how it would be, but there. So the point we're looking for here is this intersection point here. And we would call that intersection point P hit. Let's see if we can zoom in on this a bit better. P hit. That's our intersection point here. And we are going to represent it as well as P in the parametric form for the ray. P of the time t hit equals A plus the time t hit plus the time t hit times the vector c. Let's fix this just a little bit. So zooming out again here, what we're looking for is the hit point when the ray hits the line of the plane, and that'll happen at the time t hit. And so we set up a formula for t hit rather than p hit, in fact. And so that formula looks like this. T hit equals n, the normal vector, dot b minus a divided by n dot c. So b and a represent the points in each of these lines, A being the origin point of the ray, B being the point on the line, and C is the vector that the particle or the ray is traveling along. So that gives us the time, and once we've calculated the time t hit, all we need to do to finish this is to go to, well, this formula here. P hit equals, or P of t hit equals A plus t hit times C. So that's the point we're looking for, p hit. Once we've found this point, p hit, there are certain things we need to check. For instance, if we're using this as collision detection, the line that we're working with here might have actually one point B here. If we zoom in on this a bit, a point B here, and then another point, you can call it B2 here, and these are actually the beginning and the end of this line segment. So we actually need to check whether p hit has x or y values between the x and y values of b and b2, in order to make sure that the ray is not actually going something like this, direct this here, intersecting with the line here, which would give us a p hit and a t hit. However, the point would be outside the segment that we're looking at. So that's one check we need to check. Before we even calculate p hit, after we only calculate t hit here, we can do a few checks there. For instance, if we get a negative t hit, that means the hit happened somewhere behind A, meaning that it's not of interest to us when we're doing the collision detection, since we're looking forward. And also, if t hit is higher than the time, the delta time that this frame took to draw, or if we've already set the frame time up as ranging from 0 to 1, then we're only interested in t hit from 0 to 1. If we haven't done that and we're just looking at the frame time itself, then we have to check that t hit is bigger than 0, but also smaller than delta time, or the frame time that we're looking at. So make those checks while the program is finding this. If all of these checks add up, and it's actually happening within this frame, and it's also happening, the hit is also happening between the endpoints of the line that we're looking at, then we have a true hit, and then we need to go to the collision response. So here we have the collision detection. The next part would be the collision response. And in that case, we're looking at some line here, and we're not really interested in what point is on the line, but this would be the same line that has the point B in it, and we have the vector n. So still using the same vector n from the other example, since that is the surface that is being reflected off of. Then we have some vector, we can call it c. It's the same vector as the vector c from the previous example. We set it up originally calling the vector a, but what we're trying to find here is the reflected vector r, which is the new direction that our particle should take after it has actually hit the surface and bounced off. So the formula for that simply looks like this. R, and we can zoom in a bit here. R equals the vector c, so the original vector, minus 2 times the vector c dot n. Wait a minute, drawing isn't properly happening here. C dot n times n. But we have to make sure that if we use this clean like this, that the n vector is normalized, that we have a unit length n vector. If we don't have a unit length n vector, we have to make sure to normalize n first. Or this would be the same thing as saying this whole thing here divided by n dot n if we want, seeing as n dot n is the length of the vector n squared, and we have two instances of n normalized here, so we need to divide by the vector squared. So either have the vector normalized beforehand or divide by the dot product of n and n, or the dot product of n with itself. So it could look like this if you don't have a normalized vector already, or you could say if you're absolutely sure that n is a unit vector before you go in here, or you normalize it beforehand, then the formula can look like this. So here we have our formulas, the intersection and the reflection, and this should be something that you should be able to set up in your program and get it to actually work when working with a moving particle moving along a vector, checking whether it hits a surface, or checking whether it hits a line, and then bouncing it off of that line. So to explain this a bit better, we'll just start with a reflection here, and here, the idea behind this is that we're basically taking or imagining a vector here that we can call the vector c. And what we want to be able to do is to take this vector c, and we want to represent it kind of as the sum of two vectors. One of those vectors that will be parallel to this vector v, and the other one that will be perpendicular to the vector v, which means it'll be parallel to the vector v perp. And to freshen up on any properties of dot products and cross products and the angle between vectors, you can just refer to the recorded lecture on vectors. But at this point, the idea is we want to be able to say we have the vector c, and it has a specific direction, and it has these specific coordinates here, cx and cy. But we can't really, for some reason, view the vector or split it up simply by saying we can do calculations on the x coordinates separately and the y coordinates separately. What we want to be able to do is say we want to split it up into two vectors, where the vector c is the sum of those two vectors, where one is parallel to a specific other vector. And the reason we want to do this, if we look again at the reflection here, is the vector n here represents the vector v in that example. And what we want to be able to do is to take the vector c and say, can we split vector c into two vectors, this vector here and this vector here, and we can see that the first vector and the second vector, if we add them up, we have the vector c. If we can split it up into these two vectors and say we're going to take this vector here, the one that's parallel to n, and we're going to subtract that twice from the vector c, it'll end up giving us this part that's perpendicular to n the same. The other part will be reversed. So either we look at it as such that we're taking the part that's parallel to n and we're flipping it, or we're subtracting it twice. It doesn't matter. But the formula, as we can see here, views it as though it's being subtracted twice. So that's the idea behind this, splitting the vector c into two vectors, a part that's parallel to n and a part that's perpendicular to n, and then taking that parallel part and flipping that over in order to give us the reflected direction. And so we have this set up here. And since we have this vector v here and this vector v perp, we can say the vector that's parallel to v, but exactly this length, we can call that k times v. And a vector here that's parallel to v perp, but exactly this length, we can call that m times v perp. And then we can say C can be set up as the sum of these two vectors. And now the only thing we need to do is to solve for k. And if we can solve for k, then we can find this vector that's parallel to v, or parallel to n in the reflection example. And that's all we need to be able to subtract that twice from the vector c and give us our solution. So the only things we have here really now is that we know these two vectors are some scalar times v and some scalar times v perp. These scalars are k and m. We have one equation here with two unknowns. So what we need is a way to eliminate one part of this equation in order to solve it for only one of those unknowns. And in this case, we can use the fact that the dot product of two vectors that are perpendicular to each other gives us 0, and we know v and v perp are perpendicular to each other. So if we say c dot v equals k times v dot v plus m times v perp dot v, this gives us 0 in this part here. Since v perp dot v is 0, the vectors being perpendicular to each other, we've lost that entirely. So then we can just look at this part here and continue with that, saying this means k equals c dot v divided by v dot v. We can do the same thing for m if we want. We can now take the entire formula and take the dot product of that and v perp on both sides. Then we can eliminate k times v and get and solve for m. But that's not really of that much interest to us, since we can also find the second vector simply by subtracting k times v from c. But in the end, we can set it up this way. Since k equals this, we can now say c equals c dot v divided by v dot v times v plus c dot v perp. This is what we'd solve m as, actually, v dot v times v perp. And we can also switch v dot v for v dot v equals the length of v squared, if that's of interest to us at any point. And that's actually what we do in the end in the reflection formula here, is that we're actually dividing by, you can see we have two normalized n's. That's the same thing as dividing by the length of n squared. So when we set up the reflection example again, you can see that we have the inbound vector c the outbound vector r, we have a normal vector n, and we're simply taking this vector here, this part here, and we're subtracting it twice from C, giving us the reflected vector equals C minus 2 times, then we have that vector C dot n divided by m dot n times n, or in the same way, r equals C minus 2 times C dot n normalized times the vector n normalized. So this part here, since it's a dot product of two vectors, it just gives us a number. That number times 2 will be the scalar into the vector n, and that vector will be subtracted from C. So that's the explanation of this formula here. We're simply splitting the vector C in two, vectors, one parallel to n and the other one perpendicular. Then we're just looking at the parallel part and subtracting it twice from C, yielding the reflected direction. That is to say, we're projecting the vector C onto n, and the projection of the vector C onto n gives us this part of the vector here that we then can subtract twice from it in order to give us the vector r. Alright, let's move on to the intersection. So the basic setup here is that we have a point here, point A, we have the vector C, and we have a line here. And we can imagine just setting this line up. There's a line between 2 points. Let's call the points B and B2. We can use either of these points as the base point. So the point B2 becomes redundant once we set it up with a normal vector. But the idea here, if this was a plane, it could be set up as 3 points. So let's imagine in 3 dimensions here that we have a plane with 3 points. Let's call them P1, P2, and P3. What we can do with these 2 points is we can say we have a vector V1 or V2 here equals P3 minus P1. We have a vector P1 here, which equals P2 minus P1. And finally we can say the vector n, which is the normal vector to the entire plane, equals V1 cross V2, or V2 cross V1, which would give us a normal vector in the other direction, if that matters in the case that you're using. So here we can get the normal vector in this case. In the 2-dimensional case, so you don't need to stick with this here. You can just pause the video to look at it if you need more time with that. In 2 dimensions, rather than representing a plane, a point normal form represents a line. So in that case we can say, alright, we'll just set up the vector v, which equals in this case b2 minus b1, and is a vector here. And then we can say the normal vector equals the vector v perp. And v perp is simply minus v y and vx. So here we have ways to find the normal vector, to move from this two-point representation or the parametric representation into the point normal form. So we find the normal vector, and finally, once we have the normal vector, whether it's in 2 dimensions or 3 dimensions, let's just draw a normal vector in here and say here's the normal vector n, which is perpendicular to this plane here, and at that point we don't need the point B2 anymore. And the point normal form looks like this: n dot r minus b equals 0. Basically saying that this is a condition for any point r that lies on the line. If you can take that point, we can just draw in this imagined point r here, and you can make a vector which is subtracting b from r. It's the difference between r and b. That would be this vector here. If you can take that vector and the dot product of that vector and n is 0, that means that vector and n are perpendicular to each other. And since we know n is perpendicular to the line, a vector that is perpendicular to n must be parallel to the line, yielding that r is in fact a point on the line. So this is the condition that we're looking at here. So this is the point normal form we have for this line. The other part is actually a ray rather than a line, since we're looking at a particle moving in a particular direction. And we say we're using the parametric form for that line, saying p of t equals a plus t times c. Okay, so we have the parametric form for one line, we have the point normal form for the other. And what we do then is we simply find a way to solve the two together. So the point that we're interested in now is the point where this line and the other line intersect. Here. So this point here. And that's a point that is on both lines, meaning that we can get that point by putting some t into this formula, or into the parametric form for that line. We should be able to put in some t that gives us the point, let's call it p hit. So we know that there is some t, which we can call t hit, such that we can put it into this formula and we get this point p hit. We also know that if we were to put the point p hit into the point normal form, that would yield us truth, that is, it would be 0. So what we simply want to do is we simply want to say p hit equals the formula, the parametric form for this imagined time, the hit time t hit, and we're simply going to take the formula p of t hit and put that into the point normal form and solve these two formulas together. So onwards to here, set this up like such. N dot this can look better. N dot p hit minus b equals 0, and p hit is simply p of t hit, putting t hit into this formula, so that gives us n dot A plus T hit times C minus B equals 0. Then we can just move things around here and say that means N dot A minus B plus T hit times C equals 0. And because of dot product properties, we can now say N dot A minus B plus N dot T hit times C. So it doesn't matter if we take the dot product of both and then sum them up, or if we sum them up first and then type the dot product with N. This equals 0. And now we should be able to solve for T, since we can take T hit outside of this. It doesn't matter if we multiply with a scalar one of the vectors in a dot product first, or if we take the dot product first and then multiply. So we can now say T hit times N dot C equals N dot B minus A. So we moved this over, subtracted this from both sides. And finally, that gives us T hit equals N dot B minus A divided by N dot C. So here we have the formula for T hit. And as we know, our next step is simply saying P hit equals P of T hit, which is A plus T hit times C, and then we have the point of collision. As we talked about earlier, before we find the point of collision, there's a lot that the time of collision can tell us. Like, are we actually interested in it? Does it happen in the past, or does it never happen at all? Or does it happen actually within the frame time that we're looking at? So we need to check those things. Then we find P hit, and then we need to check P hit for things like, is it actually happening between the line segments or inside the line segment? If we have many things, many collisions that might happen within the same frame, we actually need to check all of these collisions. We need to take the one that yields the lowest T hit that is still within the frame time, that is bigger than 0 but lower than the time the frame took, the delta time. And you can get that from libgdx, something like gdx.input.getDeltaTime, I think, or gdx.graphics.getDeltaTime. So that delta time is the time that the frame, or the last frame, took, which is what you use as your input time into this frame and multiply all your motions with. So check that it's within that, but take the collision that gives the lowest T hit. You can imagine something like lines that are really close to each other here, and you could hit either one of them. So you're here, you're moving in this direction. You have to make sure that this is the collision that happens and not this one. So even if you go through your loop and this line is the one you check first, you have to keep checking until you find this one and say, okay, I already had a collision, but I have a collision now that has a lower T hit, which is still within the frame time. Now that's the collision that needs to happen, and this is the reflection that I need to do. Once you've done this, you also have to think about things like, and if you want it perfect, you think about things like how much time has passed, what is the T hit here, subtract that T hit from your total delta time and say, now I'm going to set my point up here and move in this direction, not the whole delta time, but only the what's left over of the delta time after subtracting the time that it already passed here, the t hit, when I actually hit. So in the beginning of the frame you're here, in the end of the frame you're here. It's okay in computer games to just say, if I hit, I'm just going to stay there. So this is where I end up in the end of the frame, even though I should be here, simply because once you test it, if it doesn't look weird or if it doesn't look jumpy, then it's good enough. In-game physics are good enough if they look good enough. But absolute perfection would happen if you take this point here, go to the hit point, start at that point again, and do the remainder of the frame time motion along the new reflected vector. That, however, means that if there was another obstacle here, you'd have to do the collision again. So this again brings up problems. So the simple way is just to always stop where the collision happened. What you'd otherwise have to do is to do the collision, update the collision direction, update what's left of the frame time, and then do the collisions again. Check all the collisions again, finding this point, updating to here, finding a new reflected direction, and then doing it again and again until you find no collision at all. So not until you find no collision can you be sure that you've gone in often enough through the loop. However, I'm saying this for those of you who want to actually do this perfect, kind of lie over this, make it perfect, and then actually point out in your code where you're doing this, because I'll give you props and credit for doing this properly. But I'm not expecting it, and I expect a lot of you simply to make this simpler for you by simply stopping where the collision happens, updating the direction. But next frame you have to move in that direction and make sure the collision happens. But just kind of set up your problem as complicated as you're ready to go through with. If you're ready to finish a full calculation like this, where all these 2, 3, 4 collisions could happen within the same frame without accidentally dropping stuff through the lines that you should be bouncing off of, then by all means go ahead and do it. If you feel like this is too complicated for you, just make it a bit simpler. And also, if you want things very simple in your final collisions, your final collision detection, if you're just using rectangular boxes that are parallel to the axis of the coordinate system, then you don't even have to go through all of these complicated things that we've been discussing. You don't need to take all these normal vectors and stuff in. You just need to say, what are the y coordinates here that I might be hitting, and what are the x coordinates here between, and does the vector that I'm moving along, will it, within this frame, can I update it to a point where it's at this y, and when it's actually at this particular y, will its x coordinates be between x1 and x2? If that's the case, then a bounce happens, and that bounce doesn't even have to use the full reflection code, the full reflection formula. Instead, you can simply say the bounce happens off of something that's parallel to the x-axis, meaning I just flip the y-coordinates. So you can make it simpler this way, but if you go into the full complicated bouncing off of diagonal lines, you will get credit for it and you will get props for it.